Great, welcome. So I'm going to talk to you today about designing rovers for other planets. I'm not a software engineer, so it's going to stray into some areas that probably you don't think often about as software engineers, but hopefully it will still be interesting to you. So in my career, I've really just worked in the space industry. I started off with a company called Surrey Satellite Technology in the UK, who make small satellites, mostly for disaster relief monitoring and climate change, that kind of thing. I then moved to Airbus, Defence and Space, also in the UK, where I worked on some more deep space science missions, missions to the Sun, missions to Mercury, a rover mission for Mars. And now I'm working for a startup, a Japanese-based company called ispace, where ispace themselves build lunar landers, and our office in Luxembourg, which is where I'm based, we focus exclusively on the rovers that would travel on those landers. So this is my first slide. I don't expect you to be able to read it. It's a terrible first slide, I apologize. But this is a little bit old now, but a pictogram of all of the missions that had flown to Mars as of about 2010. You might just about be able to make out at the end of the lines, there's some little yellow stars at some of them. Some of them have pictures of spacecraft at the end. The little yellow stars are not really stars, they're explosion marks. So about 50% of the missions that have ever tried to go to Mars haven't made it. The story is not different for the moon. This is the same kind of thing for the moon, different pictogram, same idea. The green, successful, red, less successful. You'd think that we were getting more successful in our missions, but actually with the emergence of commercial space missions going to the moon, we're seeing that that learning curve is starting all over again, and actually the statistics are still about 50-50. So space is hard. Although what I'm actually going to tell you is that space, the technology, that's the easy bit. What's actually hard is the politics. So getting to the point where you've actually got a mission, you've got all of your partners, you've got your consortium, you're launching, that bit is the bit that kills more missions than the technology does in the first place. So if only 50% are going to be successful technologically, even more than that fail, even on the drawing board, just because they haven't managed to get all the partnerships to work. So these are the rovers that I've spent my life working on for the last nearly 20 years now. So ExoMars was the first European Space Agency mission to Mars. Then came the Sample Fetch rover, which was a partnership with NASA. This was going to be the rover that collects samples to send them back to us here on Earth for analysis. I then moved to ispace, and I worked on a much smaller rover called the Polar Ice Explorer. I then spent about 6 months to a year working on each of 2 different proposals that fundamentally didn't go anywhere, so they never got named. I then worked on a small rover called TENACIOUS, that did actually launch to the moon, and it landed in April of this year. And now I'm working on a project called Magpie. So I'm going to walk you through all of those missions, some of them, and a little bit about what the context for the mission was and what the main design drivers for that mission were. But what I want you to come away from this understanding is that, yes, they're all rovers, yes, they're all going to different planetary bodies. The mission context makes them radically different in how they were designed, how they were due to operate, and all of the engineering that went into them. So I'll try to step through some of the general engineering topics and differences between them, but then sum up at the end of each one on what the implications for the software side were for each of those missions. So among these, we have a couple of awards. I just want to show you that ExoMars was the first European rover mission for Mars. TENACIOUS was the first European rover ever to launch into space. And Magpie is due to be the first European Space Agency partnered rover mission on the moon. So this is the beginning. It won't be the end. So starting with ExoMars, the one that I worked on for the longest and the one that really started my passion for rovers. ExoMars was meant to be a mission that would be looking for life on the red planet. So all of the missions that have gone before have really been looking to characterize the environment of Mars, understand whether the conditions are there to support Earth life on Mars. Could we go there? Could we grow plants? Could we find water to live, oxygen to breathe? We weren't actually looking to understand whether there was life already on Mars, and that's what ExoMars set out to achieve. It was in its latest incarnation because it went through a few iterations of geopolitics before then, but it was due to be a Russian and European partnership. So we have the rover itself, you can see there at the front. There was also an orbiter called the Trace Gas Orbiter. It was primarily looking for methane in the atmosphere of Mars because that's one of the main markers that we think could indicate life. There was a little lander that was carried by the orbiter. It was called Schiaparelli, that was to demonstrate some of the heat shields and other technologies that we needed to get onto the surface, and also carried some science equipment to monitor things like the radiation environment there. And this mission was due to launch, when I first started working on it in 2011-ish, was due to launch in 2016, then 2018, then 2022. And it was in the box, ready to ship to the Proton launch facility in Kazakhstan when Russia invaded Ukraine. And it became an embargoed piece of technology that we couldn't send to Russia anymore, and it never got to launch. So for the purposes of this mission, a European mission, you'll notice that for the purposes of space, Canada considers themselves to be European. These are some of the main countries that contributed to the mission. This is my team at Airbus. We didn't take many team photos, so this is Christmas jumper day. I particularly like Mike's suit. He was looking pretty fine that day. So there was about 160 people at Airbus alone working on the mission, but then there was all of the instrument teams, the lander team, the Trace Gas Orbiter team. We think that at its peak there were about 1,200 people working on ExoMars. Designing for Mars, you have a lot of interesting challenges, most of which you don't really have in terrestrial engineering problems. So low temperatures, its radiation is high there. You've got to land, which is always challenging for space missions. And one of the interesting ones that I think is that we're looking for life on Mars. So we need to not take anything with us that could be misconstrued as being life. So no organic molecules, wipes out a lot of plastics and things like that you could take, greases, lubricants, paints. But also when you're building it, it has to be built in such a way that it's still sterile, biologically clean at the point of launch. So we had to do a lot of things like baking them out. So literally just putting them in an oven and baking them. You had to bleach things, drop things into hydrogen peroxide plasma, all kinds of things that aren't really very good for engineering hardware, but to make sure that it's biologically clean. So some of those things were actually the kind of sizing or deciding factor on what materials we could take, what technologies we could use, was actually, can we sterilize them before launch? So to put a few of those things into context, dust. Yeah, dust. It sounds like fairly low-key, not a big problem. This is a dust storm on Mars. So 2 pictures taken 3 months apart by the Hubble Space Telescope. The first one, you can clearly see the polar ice cap, some of the large geological features, big mountain ranges, stuff like that. And then this happens. This is a global dust storm. So it starts with little sand devils in the desert, and then they gradually coalesce, accumulate into a global dust storm. And when you're on the surface, if you're powered by solar arrays and you're driving around using visual systems, cameras for navigation, this is obviously a problem because you're just driving through a cloud. You can't make any power. So when we're on Mars, we have a total orbital period, a total Mars year, about 2 Earth years. The dust season is about half of that. Now, our mission duration, as ExoMars was meant to be 218 Martian days, or sols. That's a round number. We're engineers. I don't know where it came from. So you can see that if we land at the wrong point, we can live our entire life in a dust storm. So that means we need to oversize our solar arrays dramatically. We need anti-static coatings on all of our cameras and optical surfaces. But fundamentally, we need to be able to survive and operate in the middle of some very challenging dust environments. But when we say storm here on Earth, we tend to think of winds whipping around us and breaking things. That's not really what we're talking about on Mars. There's no real damage likely to happen to our hardware because of the winds, although the wind speeds are similar to what we would get in a storm here on Earth, maybe 80 kilometers an hour, 100 kilometers an hour. But the actual atmospheric density in the Martian atmosphere is so much less than we have here on Earth. It's about 1% of the density that we have. So if you imagine a rhino running at you full pelt and bumping into you, yeah, that's problematic. But if you have 1% of the particles of a rhino, a small kitten running towards you full pelt, much less of a challenge. So nothing is going to break or fall off of our rover because of the winds. What we're actually worried about is the accumulation of dust on our optical surfaces. Temperature is also a problem. So this is a terrible graph, and I've never bothered to remake it. But time is in seconds, obviously. Why wouldn't you? We start at midnight, and we're still getting colder through the Martian night. So we start as a positively balmy minus 115 degrees centigrade, drop down to about minus 125. Then the sun rises, and you very sharply spike in temperature until you reach about -5, something like that, and then it drops away again after the midday. I've put the red dotted lines on here to indicate the standard upper and lower temperature operating bounds of commercial off-the-shelf electronics. So you can see we've got a problem here. Slide. Planetary protection. So this is me in our bio clean room in Stevenage where we were building the rover. This is the flight model of the rover. And you can see the nifty get-up that you have to put on to be able to go into the clean room. So you start off by putting gloves on. You have to put some undersuit. It's basically scrubs, like you'd have in an operating theatre, that you have to put on. You have to put them on without them ever touching the floor, which is quite a challenge. So you have to kind of wiggle around on one foot and make sure they never touch the floor. Once you've put them on, you have to take your gloves off because you might have touched your skin with the gloves, so the gloves are contaminated, so they have to go in the bin. Then you get another pair of gloves and you put your oversuit on, same thing, can't touch the floor. And you put your overboots on, you put your hood on, you put your mask and your goggles on, and then you have to get rid of that pair of gloves because they might have touched part of you. So then you put another pair of gloves on, but you might have touched the outside of those gloves with your hands while you were putting them on, so then you have to put a second pair of gloves over the top of your first pair of gloves. There's then a sign at the entrance that says, "Have you remembered to go to the bathroom?" You stand in an air shower, you get blasted with HEPA-filtered air. It all gets sucked again through a HEPA filter to make sure that there's nothing contaminating the outside of your body. And then and only then can you go and work in the clean room. Everything in the clean room has to be scrubbed down with biocides every week or so. And you have to rotate those biocides so that anything that does begin to develop any kind of tolerance to that gets wiped out by the next one. So this is a challenge that not many people have to worry about. Entry, descent, and landing. You start hitting the atmosphere ballistically, supersonically, and the only thing that you can do, because there is an atmosphere on Mars, it is going to heat you up, is have a heat shield and hide behind it. So although there is an atmosphere, there's actually not enough atmosphere between the top of the atmosphere and the plateaus and the highland areas for you to be able to land there with a parachute at all. You don't have enough time to slow down before you hit it. So we can only actually access the lower areas, the old sea areas of Mars, where the altitude of the ground is lower. So you go in with your heat shield, you drop from supersonic to subsonic. you can then deploy a very small, very robust parachute until that brings you down to a slower speed where you can deploy a full-scale parachute. You then have to do two things pretty much simultaneously, which is to jettison your heat shield, jettison your back cover, and fire your retro rockets. So you have to fire these rockets in the direction of travel that are going to bring you to a hover, slow down your speed enough that you're actually stationary, and then you can gradually decrease the power that they're putting out to bring yourself down to the ground. If you use them to get you all of the way down to the ground, because there's no launch pad there or landing pad, nothing that's even predictable in terms of what's underneath you. If it's soft sand, you could dig yourself a hole, and then your rover might never be able to get out of it. So we can't bring ourselves all the way down to the surface. We actually have to bring ourselves to a hover maybe 1.5 meters above the ground, and then turn off our retro rockets and just drop the rest of the way to the ground. So it's not a crash landing for the rover, but it's definitely a bump landing. So that's challenging as well for some of the more delicate instruments on board. Then, a little like a flower opening its petals, the lander unfolds all of the different kind of petals around it, and the rover can use one of these ramplets to egress onto the Martian surface. Radiation is pretty bad. So on Mars, you have some atmosphere, but it's not really protecting you from the radiation environment in space like our atmosphere does. And there's no real magnetic field either. So where our magnetic field helps to bounce all of the radiation particles off, and also you end up with these charged fields, the Van Allen belts going around the Earth because of the magnetic field of the Earth. You don't have that on Mars. So everything is really hitting you on the surface. And because it's a long mission, it's 218 Martian days, you have enough time for this radiation damage to accumulate. So there's kind of two different ways that radiation is going to damage you. One is the long-term degradation that you get from ionizing radiation bombarding you continuously. And the other is what we call heavy particle events, single event upsets. So things like cosmic rays hitting your electronics can cause a change of state, switch a 0 to a 1. It can also damage your solar arrays. You can get latch up. So we have to have radiation-tolerant devices in the first place, but also what this really means is that we need a lot of redundancy. So everything that we take, we have to have a spare one. In all of our data storage, we use triple modular redundancy, so you keep everything in triplicate, and before you use anything, any part of your code or any part of stored memory, you compare all three of these versions. If there's one that has a discrepancy to the other two, it's probably because of radiation damage. So you can chuck that away and use the one where you have two that match. And just hope that you never have exactly the same radiation damage on two different versions at the same time. So in terms of software, what does that mean? How do we design our software? So radiation damage means that we need to have triple modular redundancy on most things. But because it's a very long mission, we also have the benefit of time. Things don't have to be done fast, but things do have to be done safely. So we don't have to drive very fast. We don't have to do all of our science operations very fast. We can do things at a very sedate pace, take our time and make sure that we never put the rover into any hazardous situation. But we have to do most things completely autonomously. There's a signal delay to Mars, depending on where Earth and Mars are in their orbits, of between 4 and 24 minutes. So that means that if you were to be driving by teleoperation, you say, okay, beginning of the day, take a picture, where am I? 24 minutes later, a picture would be taken. 48 minutes later, you'd have that picture, and then you can decide where you want to drive. Because you're being very careful, you'd probably only decide to drive maybe 50 centimeters or a meter, something like that, then take another set of images. It would be hours before you'd gone anywhere. And that's assuming that you have live connection. Actually, a lot of the time, the rover is going to be on the far side of Mars to the Earth, so you don't have any direct line of sight. So we can only communicate via our orbiters. And there are only a couple of orbiters active around Mars, and they're not always within sight of the rover. So a lot of this stuff has to be done by store and forward commands, not actually live. And you'll just say, OK, this is your next waypoint that you need to drive to, or we want you to do a drilling operation or whatever. So all of that stuff has to be completely autonomous. We have to store and process a lot of science data on board. I think we had 14 different science instruments on board. All of that data has to be compressed, processed, prioritized for download. And it's an ESA mission. So European Space Agency, it's taxpayer funded by taxpayers all around Europe. And failure is not an option for them. Because we're using taxpayer money, we really have to make sure that everything is going to work perfectly. Because the budget, and this is before the latest hardships for the project, was 1.6 billion euros. They're expecting it to work. But it does mean that you've got a lot of budget with which to do testing, with which to do your development. So you can really make sure that every single I is dotted, every T is crossed. So in terms of the main software development for ExoMars, that meant the autonomous driving. So there's a bunch of different steps that we have to go through to make that work. First of all, you need to know where you are. We can do that sometimes from images from the overhead orbiters. You can actually see the rovers sometimes, but a lot of it has to be done by the visual odometry that you can get from your onboard cameras, and then things like wheel odometry, how many times your wheels have rotated since you were at the last place that you knew where you were. You can use your cameras on board. We have stereo cameras in the mast of the rover, so you take a bunch of pictures. You then work out the disparity between those images of the different rocks and things like that. And then you can build up a digital elevation map of what's in front of you. Where are the steep slopes? Where are the obstacles that are too big to traverse over? You can categorize those into different levels of risk, from completely stay out, this is far too big, to it's a little bit sketchy, right the way down to fully safe. And then you plan your path through that to reach the waypoint that you've identified from orbit, which is where you want to go to. So maybe it's an interesting ridge line or a crater or something like that. So putting this all into action, you start your drive. Black means you can't see it yet. Blue is the edge of your visible area. White is a stay-out zone that you've placed around the dangerous objects. And then you have a gradient from red of danger all the way through to yellow. And you plan this little black line is a meter of traverse for the rover that it's going to drive before it stops again, takes a new set of images, and then builds up the next meter. So we keep doing this in steps. And we travel through our terrain until, in this case, you get to the corner of the room that we were doing the testing in, and you can see the perpendicular walls at the corner of the room there. And you can do this right the way across the lunar surface. The only problem is, in sand, you might be slipping, you might think that you're driving, but actually you're not moving forward. Your wheels are stuck against a rock, and they're spinning, but you're not going anywhere. So you also need to make sure that you're not sliding down a slope or just about to skid off the edge of a cliff into danger. So we also have this system. So you're mapping 1,000 points onto the visible terrain. Here there are more trees than we expect to see on Mars, but the same idea works. So the red means it's close, the blue means it's far away. You track these interesting points, visible artifacts in the picture in front of you as you travel through it, and that helps you to understand whether you're sliding, and you can auto-correct your driving by applying more force to a different wheel or something like that as you go through. So this is what it looks like in the Mars Yard test facility in Stevenage. So as I say, it drives forward a meter, takes a bunch of pictures, plans another path, takes another bunch of pictures. You can see the little head turn around. It looks a little bit like, what was that? Was that an alien? No, it's my colleague Brian. There's no solar arrays on this rover, so it has to be powered by umbilical, and we had to make sure that it wasn't going to drive over its umbilical and stop itself from working. So it keeps doing it right the way across the surface. And you end up with a rover that looks like this. So we've got a drill on the front of the rover, which is how we're going to detect life. We can actually drill up to 2 meters below the Martian surface. And that's where we expect to find life if it's still there. Anything at the surface would have been so heavily irradiated over the millennia since we think that there was water running there or whatever, like that you wouldn't even be able to detect that it was organic in the first place. It would have broken down to the point that you couldn't recognize it. 2 meters below the surface, you're protected enough from the radiation environment that you would expect to still be able to at least identify that it's an organic molecule, or maybe even have something that's still living there. On the back, there's ground-penetrating radar, which help us to see the different strata between rocks, maybe detect water below the surface, and find other places that's interesting to drill. You've got 6 wheels, each on what we call a rocker-bogie pair. So that helps to keep all of the wheels in contact with the ground, no matter what the shape of the terrain. And then a lot of solar arrays to collect all of the energy that you need, as well as your panoramic cameras at the top of the mast and other cameras lower down. As I mentioned, it hasn't launched yet because of the conflict in Ukraine, but we are working on a new lander system. Russia was meant to be providing the lander and the launch vehicle. So now in Europe, we're building a new lander vehicle, but that's not a couple of days worth of effort. That's quite a big undertaking. So there's a huge delay associated with that. And we still need to find a launch vehicle that's going to take us as well. So one day, ExoMars will fly, and then that decade of my life will have not been for nothing. But right now, it's fine. It's fine. Next, I moved on to the sample fetch rover. It's also a mission for Mars. So surely it's very similar. Well, yes, but no. This was quite an elaborate plan for a mission. You can see all of these different elements are different spacecraft, effectively, that have to do different things to get a sample from Mars back to Earth. So it starts over here with the Perseverance rover. It's on Mars already, collecting samples from interesting science locations and caching them into little hermetically sealed tubes. Then there would be the launch of a rocket with the sample fetch rover on it that would land, drive to the locations where those samples have been cached, collect them and bring them back to a special lander launcher vehicle that would pack them into a basketball-sized ejectile, eject that into Mars orbit, where it would rendezvous with an orbiter. The orbiter would bring it back to Earth orbit, and then it would re-enter. Straightforward, right? So we start with Perseverance, we cache some samples, it drops them on the surface in known locations. They have to be mapped known locations because dust storms could cover them over and then they would be pretty hard to find. You need to know where to look. A lander lands with the rover on board on the top in this particular scenario. The rover drives to those cache locations, picks up the sample tubes, returns them to the dual-purpose lander launcher, which puts them into the little basketball thing, launches the basketball into orbit, and that comes back to Earth. Now, that sounds straightforward, doesn't it? That brings in some orbital dynamics issues, because both the Earth and Mars are orbiting constantly. Every roughly 26 months, we come into alignment. So you have a launch window about every 26 months. So the idea is that you launch when the planets are close together, because if you launched while it's the other side of the sun, it's going to take you literally years to get there. But that takes about 6 months still to get to Mars. Then you have to land, do everything that you want to do, and then you have to make the right launch window to come back again. So that means if you want to use the next opportunity to come back, you only have about 6 months to do your surface operation. So that means you need to be able to drive to these sites. You don't know exactly where you're going to land. You maybe have about a kilometer of accuracy in your landing. So we could have to drive a kilometer to even get to the place that we expected to land. And then we have to be able to drive to all of the sites where our cached samples are. So basically, the rover has to travel a lot faster than ExoMars was ever intended to. With ExoMars, we never expected to exceed 4 centimeters per second, which is pretty slow. That's why it was a sped-up video. That was real speed that the rover would be traveling. Sample Fetch rover would have to travel a lot faster than that. So we had to have much bigger wheels. We had to have the autonomy was able to update much faster so that we could keep driving at a much higher speed. One of the interesting things from this mission as well is that whilst we have to make sure that our mission's completely biologically clean to actually get to Mars so that we don't contaminate the samples, we're even more worried about back contaminating Earth with potentially still alive Mars bacteria. So we had to have, this is the basketball that I mentioned with all of the tubes on board. We actually design it for a crash landing. So it's basically an engineered meteorite. Even if it hits the ground absolutely top speed, terminal velocity, it has to still be completely intact and sealed, and nothing can enter our biosphere. So what we end up doing is designing a self-righting shape. So no matter what shape you enter the atmosphere with this, you are going to self-right to have the heat shield side facing downwards. It's going to be self-stable. That'll bring us to a terminal velocity that's survivable, and then we impact in the desert. It was actually due to land somewhere in Australia. So that's one of the big challenges of the overall mission and interesting parts of the overall mission. Nothing to do with the rover, though. But the rover also has to do all of the sample tube acquisition completely autonomously. So not only do you have your navigational autonomy, which now has to work a lot faster, you also have to be able to collect the tubes completely autonomously. So that's one of the big software developments that we had to go through at Airbus. So this is a much more basic mission. We don't have lots of different science equipment on board. The only thing we have to do is collect the sample tubes. But again, everything has to be automated. This is a taxpayer-funded mission for both NASA and ESA, so failure is really, really, really not an option. But we know where we're going. We know where the sample tubes are going to be, so we can plan a lot of our route before we get there. And there's a rover that's already been there. So not only do we have just the maps that are available from orbit, we can also use the images that it collected from its onboard cameras to understand what the optimum routes could be to get there. So we have to have a lot of different autonomous functionality. We still have to have fully redundant systems, but we can do a lot of the planning of the mission before we get there. And we end up with a rover that looks like this. So this time 4 wheels, they're much bigger so that we can travel faster and we can traverse bigger obstacles. They're actually made out of a kind of chain mail, which is flexible, but allows you to get traction as you climb over rocks. Again, powered by solar panels on the top. You've got a sample acquisition tray here and the cameras on the top that help you to see longer distances so that you can plan your traverse. Unfortunately, after 2 years of working on this, NASA decided they didn't want a rover after all, and they're going to do it with helicopters. So that mission never launched either. Then I moved to a new company, a company called ispace. It's headquartered in Tokyo. It was actually part of the Google Lunar X Prize, was really where my company began. We started by competing in that. We were one of the final 2 competing companies, and then pivoted the model of the business slightly to go into lunar landers and transporting stuff to the surface of the moon. So we have a Tokyo office that builds landers, an American office that also builds landers, but for the US market. And then in Luxembourg, which is where I work, we have an office focused on building the rovers that would travel on either of those 2 systems for those payload customers that want mobility on the lunar surface, so actually want to go to a specific location or travel around to multiple locations on the surface to do whatever it is that their instrument or payload does. So the moon is in some ways quite similar to Mars. It's very cold. It has less gravity. We have about 1/6 of the gravity on the moon that we have on on Earth, whereas on Mars it's about 1/3. It can get extremely hot and extremely cold, even more so than Mars, because you don't have the atmosphere working as any kind of insulator. There's no convection of gases, no wind to blow past you to cool you down, but also no atmosphere to keep you warm at night. And then we have the lunar day and night cycle. So as you know, the moon orbits the Earth every 28 days, and about half of that we're in sunshine and half we're in darkness. Whereas on Mars, it's about 24.5 hours, Earth hours, in a Martian day, so you have about a 12-hour day-night cycle. We can survive that with batteries. We can't survive, at least at a small-scale rover level, with batteries on the moon for 14 days. You'd have to carry so many kilograms of batteries for a tiny vehicle that it would make the vehicle effectively redundant. You wouldn't be able to carry anything else. So most of our missions are, at the moment, designed to just survive one lunar day, which means that you've got to do everything very fast. You've got to be very confident that you're going to do it during the time that you've got there. But you don't have things like the radiation cumulative damage, because you just don't have that much time for anything like that to really come into effect. So we've been designing lunar rovers for over 15 years, and the first one that we sent launched December of last year and landed on the surface in April of this year. It is there. It's on the surface of the moon. Unfortunately, it landed a little faster than it was intended to, so it never got the chance to operate. But much the same as at Airbus, we have a team of individuals working on it. We also have a lunar terrain instead of a Martian terrain. And we design our rovers to be fully self-powered with solar cells. It communicates via the lander. So we have a Wi-Fi link to the lander, and then the lander acts as the relay down to Earth. But because we're a commercial company, we're trying to do things much quicker, much cheaper, and in a slightly more risk-tolerant way than space agency missions tend to be. So we use a lot more commercial off-the-shelf hardware and then just test it to make sure that it's robust to survive the conditions that it's going to see. So from a software perspective, that means that we don't have as much redundancy. We don't have very much autonomous functionality, because the moon is only 1.5 seconds of signal delay away, which means that we can really take the opportunity to drive by teleoperations a lot more. And actually, that's considered to be much safer than trying to build in loads of autonomy and do complex procedures entirely autonomously when you can just have a human in the loop. We've only got one lunar day to do everything that we're going to be able to do, so there's a lot less emphasis on radiation damage. And it's a commercial mission. We're really at the beginning of the commercial space race. So we're trying to develop rovers and show that they can work. We're trying to demonstrate that we can drive around on the surface, but really any amount of success is still a success for us. So it's a lot less where the ESA missions, you have to last for 218 days and you have to do all of these things while you're there. Otherwise, the public might not consider it to be 100% successful. Really, we're looking to be able to do a small amount of things very quickly and very quickly declare a mission success. Really, our payloads are the people that are paying for the mission. They're paying for the service of being transported to the moon. So as long as we've done everything that they want to do while we're there, it's a successful mission. So this is the team that was going to operate the rover on the surface. We had 4 people on console, 4 shifts. And we were going to be operating it around the clock, as I mentioned, by teleoperations rather than autonomous control. Also, as I mentioned, we didn't get the opportunity to do that. So now I'm working on another mission, my final mission for the moment. And this is called Magpie. I can't tell you much about it because it's still under development and we don't want you to steal all of our secrets. But suffice to say, it's going to be the first European Space Agency funded rover mission on the moon. It's due to launch in 2028. And so we're really the first, what's called low-cost mission for ESA, trying to go to the moon. So this is ESA trying to do things the new space way, trying to do things fast, trying to take more of a risk-tolerant approach. So it's a learning curve for everyone. It's where commercial space meets institutional space. And we're trying to demonstrate value for money for the taxpayer whilst accepting that we're going to use a lot more commercial hardware. An element of failure is still acceptable, and we don't have as much redundancy. We don't have to operate for as long, but we do have to operate, and we do have to show that this is a good model for the European Space Agency to continue working with. Also, it is the first mission that's taking this approach, so it's very high visibility. So we've been told by the director of ESA that whilst we're taking a more risk tolerance approach, you're not allowed to fail. So, cool. But with respect to the Mission 2, which is our very tiny rover, we are still trying to do much more ambitious science. It is a European Space Agency mission. We're trying to do real interesting science at the lunar South Pole, understand whether there is water ice at the lunar South Pole, characterize the environment for future missions, understand the geological processes that have created the moon, and whether there are the conditions to support astronaut missions there in the future. So we do have to have some autonomy to be able to increase our traverse efficiency and stuff like that to get to the science targets that we need to during the mission. So very different missions, very different scales, very different budgets. The budget for these rovers is less than 1% of the budget for the ExoMars mission. Very different durations. We're only lasting for 8 to 10 days of actual operations rather than 218 for ExoMars. Very different radiation because of that. So there's a lot of things that are same but different depending on what the mission is. So I hope that was an interesting whistle-stop tour through how to build rovers for different planetary bodies and what that means for the mission. I'm happy to take questions afterwards, but I think we are either already over time or very much at the end of the session already. So thank you very much for listening and for your patience, and I hope to talk to you afterwards.